So in this video, we're going to do a couple of things. First of all, I've been pretty busy this past week making modifications to the system. I found out a couple things, and we have some different looking components than before, so we're going to go over that, what all's happened since the last video. And then we're going to go over the introduction to the first lecture, where Tesla gives some theoretical considerations when observing the phenomena occurring around the terminals of our secondary. So it's going to kind of help us get a better picture in our heads of how to be perceiving the phenomena that we visualize around this high voltage transformer. And then we'll probably just do some preliminary experiments here just to show kind of what this setup is capable of and what it's doing. So let's get going. Okay, so first things first, here is our new variable capacitor. You actually see here we have two different kinds of variable capacitors. This one is not currently hooked up, but I've been testing it out and it works pretty good. This is the high frequency capacitor that I use, and this is more for lower frequencies here. But what we see here, this is a high voltage vacuum variable transformer. So just by turning this knob here, you can adjust the capacitance between the two terminals here, between 0 and 500 picofarads, which is not very much. So it's really only for very high frequency operations, actually higher frequency than this coil is really, it's higher frequency than you should be driving this coil with. So I did have to include some biasing capacitors there, just smaller ones, but it just makes it so that we can operate within the operational frequency of this coil here when we have the balls on, or if we take off these large balls on the secondary, we can actually get this thing at a pretty high frequency, which is more suited for this capacitor. As you keep loading on more and more capacity, the effectiveness of this variable capacitor diminishes. So really this is for like high frequency stuff only. But this right now will work just fine for what we're doing. This is the other variable capacitor that I built. You can see here we have different sizes of capacitors here. So we can go from very small capacity, like here 0.5 nanofarads. If we want to increase it, we can go to 1.5 nanofarads or 2 nanofarads, or if you want to go bigger, to 3.3 nanofarads. So this is just a much easier way to swap capacitance in and out of the circuit. And I have been doing some experimenting. I was wondering how connecting all of the other sides of the capacitors in parallel was going to affect the performance. So let's say, even though we only have this one capacitor locked into the circuit, we still do have these capacitors, one terminal of each of these capacitor combinations connected to the circuit, because there's only one side of each capacitor is connected to these switches. And I was just wondering, because we're doing pulse power with this system, if that would largely affect our results, but it seems to not have that great of an effect. So basically, if we have all these capacitors switched out and this one switched in, the frequency of the primary is determined largely just by this one capacitor, and these don't seem to have that much of an effect on it, which is good. That was kind of what I was hoping for. But when you start working with high frequency stuff, sometimes you find, even though you don't think something is connected to your circuit, it actually is. So that was just good to find. This is the new spark gap that I've been using for a little bit. So what happened was, with the old spark gap that I had, I was using it with this capacitor combination, driving the transformer here. I just have the transformer out of the box right now because I was seeing some arcing when I switched to this new spark gap, and I wanted to run it with this thing out of the box for a little bit, just so I can observe, you know, a little more in detail what's going on with this thing. But yeah, I was running this capacitor combo with the old spark gap, and I had the spark gap cranked, you know, turned pretty far to where I was getting really large current injections into the primary circuit. And suddenly the thing stopped working. So I kind of assumed that that was due to putting too much current or too much voltage across these capacitors. And then when I switched this one in, it still didn't work. And now I was thinking, well, what the heck is going on? Turns out that when I opened up the gap really large with that spark gap, something happened in the wood that created a conductive path between the bolts, which are in the wood connecting the copper pieces to that wooden part. So now the thing that was mounting my spark gap pieces was actually creating a conductive path between them. And you can never really build any potential across that. And it basically just wasn't working at all. So yeah, I determined that it was actually the spark gap that went bad. So this is my new sort of replacement spark gap. It's just 2 screws mounted to this PVC pipe. And then on the end of the screws, I have these spherical ball terminations. And you can adjust it really easily just by going in there and, you know, screwing it out or screwing it in. But you get pretty fine spark gap adjustments like that. The other benefit of this is that you have a spherical surface on the end, and you don't get the charge leakage coming out of the sharp edges that we had out of the copper tubes. So that's beneficial for the spark gap design here. It's ideal to not have any sort of sharp edges on the striking surface for your spark gap to reduce charge leakage before the actual breaking occurs, or the breakdown of the dielectric. And then I think I've shown it in some other videos, but I never really showed it. This is just something I have for mounting different secondary terminal configurations. So it just connects to the high voltage output here of the transformer, and you can just sort of hang whatever you want on here. We're going to be doing some experiments today with placing balls on the secondary, so I just have that hooked up right now. We'll just do a quick little demo just to show, you know, kind of how it looks. So same thing, just turn on the breaker, flip the switch. Let me just see how wide that is. That should be good. Big, but not too big. All right. So we can see the spark gap is firing. I'm going to turn it up. You can come here. So yeah, that's pretty much it. Now I'll just show you really quick. Let me turn it off and just discharge anything that might be on there. To adjust it is really easy. You just come in here, so we'll just put it open a little more. So now we'll get some better size discharge effects. maybe about that much would be good. And let's flip it on again. So now it's jumping that without my help. So there's just a little look at the setup, but yeah, this is a pretty good experimental setup so far. I've just been doing some testing ever since I got it all together, just to make sure, you know, nothing else is gonna go breaking on me real easy. I can push this gap pretty far and everything still works. I was getting some issues where I opened it up too big, where I was getting some more arcing here on the transformer. That's why I took it out. And I've been kind of reinforcing the connections with more insulation. That's why you see all this tape everywhere. But so far, it's working pretty good. So now we'll go into some of the theory here at the beginning of this Tesla lecture. Okay, so like I said, now we're just going to talk a little bit about some of Tesla's ideas that he shared going into these experimental demonstrations, as just sort of a stimulus for how to be thinking about them, or some sort of, to give the audience some sort of geometry for how to be considering the perceived phenomena. So basically he talks about, you know, what electricity is, or some ideas that he has about what electricity is and what causes it. The first thing he talks about is how the existence of the ether, or the wider spread acceptance of the idea of the ether as being involved in electrical phenomena, has greatly overcome a lot of the difficulties in conceiving of electrical action as there were before, where the ether didn't have such a prominent spot in the electrical sciences, and the theories that were developed were a little more fantastical. But what he talks about is, he mentions this idea that he does think of all electrical interactions as being ether phenomena or ether interactions. And he talks about the electrical effects as being due to different modalities of ether. So he talks about static electricity as being due to tensions in the ether, and effects of dynamic electricity or electrical currents as being due to ether in motion. So you have this duality of ether under stress and ether in motion. And those are kind of the two sides of the electrical coin, so to speak. Now, how this actually happens, what this actually looks like, you know, that's still a little bit mysterious. One thing he does indicate is that it was known at the time that electricity behaved like an incompressible fluid. So this is basically saying, you know, it can't actually compress or expand. So what does a strain or a motion look like in this conception? That's kind of what he's talking about. He does kind of allude to the idea that a lot of the popular theories at the time, and even now, talk about the two electricities theory, or this idea of there being two types of electricity equal and opposite to one another. So what this is referring to is pretty much like what we talk about nowadays, where we have like protons and neutrons, or positive charge and negative charge, existing as two separate entities, which neutralize each other due to their equality of charge. And he says it's kind of tempting to consider, because it seems pretty simple to explain a lot of phenomena with, but the simplest explanation of a phenomena is not necessarily the correct one, and it can lead to a couple pitfalls there. What he talks about is, if there is something called electricity, there can only be one of it, and a want of it or a excess of it. So what he's talking about here is, instead of having, a charge here that's positive, and let's say another charge here that's negative, what he's talking about is, if we had, let's say, a box of substance here that's dispersed evenly throughout this box, that would kind of correspond to a neutral charge or no charge. And if you were to create some sort of displacement or movement away from equilibrium in that box, so let's say you take the contents of that box and kind of force it into this corner, and you create an excess of contents in this corner and a sort of lack of contents in the other areas of this box. So that would be creating this sort of positive and negative charge, even though there's not two different entities involved. It's only one thing that's sort of moved and distributed in different ways, which sets up the pressure conditions for their equalization. So that's kind of what he's talking about there with that one fluid theory. Now he talks about what actually is electricity. And he says that it's kind of tempting to call electricity ether, but what he mentions is that we really have no evidence of electricity, and you have no hope of obtaining that evidence unless gross matter is present. So what he's kind of conceiving of when he talks about electricity is that it's ether associated with matter. And that is you have some sort of molecule or something right here, and surrounding that molecule you'll have some sort of bound ether. So I'm kind of picturing like you have this, that's maybe not the clearest drawing, but you have a sort of whirlpool of ether around this molecule, sort of moving along with it wherever it goes. And that ether circulating around that molecule is considered as bound to that molecule. So you can kind of think of this as like, if this molecule would be our sun, we have all these other celestial bodies and galactic currents that are orbiting around that sun. So they're kind of bound to the sun in the same way that ether would be bound to the molecule. So it kind of travels with it wherever it goes. And that is what he says constitutes the electrical charge of the molecule. So he kind of considers the electrostatic action to be involved in all molecular actions. He talks about also how if you take a charge, which is stationary, and you move it around in a room, you obtain evidence of electrical current. You get the magnetic effects that would be associated normally with an electrical current. And he kind of talks about how he attributes all action, all electrostatic action, electrodynamic currents, and even permanent magnetism, he actually just attributes as being due to the electrostatic charge around the molecules. So he's kind of picturing of, electric potential as a measure of the strain due to the motion in the bound ether, and then the magnetic effects is being due to the actual sort of orbital or translational motions of this molecule and its bound ether. But it all can really be traced back to the electric charge associated with these molecules, or the electrostatic force of these molecules. Okay, so here I have the 0.5 nanofarad capacitor locked in. We're just going to power it on here. We have a very small distance in between our output terminals, or the balls connected to our output terminals. And we can see we're not getting any action between the spheres. So now if I turn down the power And now I'm just going to go ahead, turn that off. Make sure I discharge anything. Okay, now we're going to switch this out. Just a little close to that wire there. Now we're going to swap in a 1.5 nanofarad capacitor. So we're just going to go a little bigger now. So we just have a little bit more capacity in there. We've increased the charge injections into our primary and have decreased the frequency. So now let's see what happens. We immediately, you can see just by doing the capacitor swap, we immediately get some more prominent effects on the output. I'll try to get a little closer here as I'm still on the controls. Okay, now let's just bring it up a little more. Or I'm sorry, down in frequency. We're going to swap that out. Swap in the 2.3 nanofarads. Okay, we're going to look at the output. All right, now we can swap in an even larger capacitor. I'm still really zoomed in. Okay, so what we've done is we started above the resonant frequency of this system, and now we're moving down in frequency. Let's see what this does. So one thing we can notice with this larger capacitor, we notice immediately just by the sound of it, the slower rate of charge and discharge through the primary. You can actually hear all the individual discharges occurring. All right, we're going to drop this even more now. Now let's see what happens if we really add some capacity on the terminals here. So we're just going to add this one, and that one. So now we're pretty well below our resonant frequency here. Let's see what kind of effect that has. Let's see. I did notice when I tried to do, so I've never tried that before with 4 capacitors hooked in at once, but it seemed like the charging current required to build the potential across these capacitors was like too much for it. So maybe best to keep it to 1 or 2 capacitors at a time. But we saw what happened as we swept down in frequency. Now we're gonna increase the distance between the spheres a little bit. Because what happens when we put them so close together is we actually restrict the amount of voltage that can develop across these, so we won't get that great of effects on the output necessarily. So now I've put pretty good distance in between these things, maybe 1.5 inches, 2 inches even. We're going to start, we did our high frequency. We kind of saw how that went. We're going to go at 1.5 nanofarads now, which is below the resonant point. I'm sorry, above the resonant point. So we're going to turn this up, see how it goes. So we can see we're getting no effect. We're definitely going to be getting some output. So we're getting some high voltage on there, but it's not enough to jump our gap. So we're going to swap in now to 3.3 and turn her up. I am noticing that this spark gap does have some issues with not breaking. So once it establishes an arc, it doesn't actually break the arc. So that's what happens when you hear it. You hear it kind of popping, and then you'll hear the sound even out. What you'll observe too when you look at this is the color goes from a whitish discharge color to sort of a purplish stream. And it sounds more like maybe like a gas escaping. It gives that sort of sound as opposed to like that discontinuous popping sound. And you notice that when it makes that sound, you lose all your voltage on the output terminals. And that's because the arc actually is not breaking. It's a continuous arc. So that really restricts the amount of charge injection you get into your primary. It takes us from being a disruptive discharge to just some sort of weird continuous current device. So we don't want that. Some things to do to fix that. We can just try moving these out a little bit. Now I know Tesla spends a lot of time talking about improvements made to his spark gap to try and extinguish the arc as soon as it's initiated. So I'm going to be looking into that later, but for now we'll just increase the distance between the two. This will give us better breaking of the arc, and it will give us a higher charge injection into our primary just because of the larger gap size. So now I would actually expect this thing to start arcing over from ball to ball. Oop. We got a quick spark. So there we go. We can see that separation there improved our performance quite a bit. I have learned, it's all fun and games, trying to push that gap as wide as possible, but you blow a lot of devices that way, and after a while you get sick and tired of it. So I'm trying to be a little more on the conservative side now with this thing. But that's just kind of a look at our capacitor bank and the setup we got here. So now we'll start looking at these different discharge phenomena with the two spheres. So basically the way that we're thinking about this phenomena is here we have our two high voltage output terminals, which are being charged alternatingly, positive and negative with high potentials. So what that's doing is it's creating a activity in the space between these spheres all around it, but predominantly in the space between the two spheres where the motions are strongest. It's creating a molecular bombardment where the air molecules and whatever it is that's in between these are being basically made to bombard each of these spheres here. And it's this bombardment by the air molecules, which is the cause of these visual displays that we're seeing here. So he is trying to say that when you interpose dielectric material in between these things, you're changing the properties which exists where this molecular bombardment is occurring and where these inductions are occurring. So you're changing the character, I guess, of these bombardments or you're changing the properties of the medium, I guess, where these inductions are being created, which will correspondingly change the visual or the appearance of sparking and things like that. Okay, so now we're going to get this going, and I'm basically going to have it set up to where it's just about to produce a spark between the spheres, but not quite. At that point, I'm going to drop down this piece of glass in between the spheres, increasing the inductive capacity of the medium between the spheres, and we're going to try to induce a spark to jump because of the increased tension created by the addition of this glass pane in between the spheres. So I'm just going to get it going. You see no breaking right now is occurring. We need a little bit more. We've got to get it right on the cusp. Try this. So we did see that I was actually able to successfully induce sparking in the balls by the interposition of the glass pane. And it's a little inconsistent because no matter how hard you try, you just can't get those things to sit perfectly straight. So there's just a little bit of swing. So the distance between them is constantly increasing and decreasing at a pretty slow rate. So it makes it hard to induce a constant spark. Also, what I've noticed with the experiment so far is that if you get them perfectly still and you get sparks arcing between the two, if you kill the power, you'll notice there's a little bit of movement there. So there does appear to be some movement that gets induced just by the act of the discharge between the two. So we can try it again real quick just for another demonstration. So again, you have no arcing. And we can see once again that just by interposing the piece of glass in between the two spheres, we were able to create the conditions for that discharge to occur. So we saw that by interposing the dielectric material between the spheres on our output, that we were able to change the character of the spark discharges in the airspace between the spheres and the dielectric. We increased the inductive capacity of the medium by this interposition of the dielectric material. So we saw that if we lowered down the glass in between the spheres, we could actually create the required capacity for the spark to form in the first place. And we see it's tempting to think that the spark is passing through the dielectric, but it actually is occurring on either side of the dielectric, going from dielectric to sphere. And this is something he talks about here, where he says, it appears almost as though these streams pass through the dielectric. In reality, this is not the case, as streams are due to the molecules of the air which are violently agitated in the space between the oppositely charged surface of the spheres. Then he says, when no dielectric other than air is present, the bombardment goes on, but is too weak to be visible. By inserting the dielectric, the inductive effect is much increased. And besides, the projected air molecules find an obstacle, and the bombardment becomes so intense that the streams become luminous. So pretty much what we're getting at here is that there is an activity happening in the airspace between these two spheres. And it has to do with alternatively charging and discharging molecules, causing them to sort of bombard each sphere according to its potential, with respect to the potential of the sphere. And when we place a dielectric in there, the material that the dielectric is made of is also being charged, or I guess polarized would be a better way to describe it, but the material is getting charged essentially by the electric action between the spheres. And that charge on the dielectric is helping to accelerate or I guess to increase the inductive effect between these two spheres. Maybe that's not a common conception of how the action of dielectric materials works, but a good experiment that I'll do again when I get this thing put back into the box is if you have this high voltage terminal and you're running your unit, you can actually place a glass cup over the high voltage terminal so it's not touching anything. So all contact would be inductive, but you can draw sparks off of the glass cup because the dielectric material itself is actually being charged by the high voltage terminal through the capacitive connection. So when we put the dielectric material in between there, we're actually charging that dielectric material as well. And that's helping to increase the effects we observe between the two spheres. And this video is getting kind of long at this point, but I think for the next video, well, first of all, I want to work on the spark gap a little bit because it's giving me some issues. So maybe I'll have to do some videos where I try to improve the design of the spark gap a little bit, because that is kind of restricting. You'll notice during some runs, it'll just sort of give out and it kind of stops discharging disruptively, as you just have a constant arc going across these two. That happens when the arc goes from a white color to a purple color. So this kind of needs to improve a little bit. But I think next video we'll maybe do some more in-depth analysis of what's going on when we increase or when we change the dielectric properties of the medium in between the spheres. Maybe do some VNA analysis, and we'll look at some oscilloscope plots again.